All right, guys. So we are back, and we are going to now look at functions and relation. So I was saying before that coordinate geometry and graph, they have a connection, and so functions and relation also have a connection to those two topics. Now, in fact, functions and relation it is graph same way, but we are looking at this topic. We are looking at it in a more formal way. So now we want to define the equations that we plot on the graph. We want to define them either as a function or as a relation, right? So we need to make a clear distinction what we refer to as a function and what we refer to as a relation. So this is what this topic is all about, but it is still referring to equations that we would normally plot on a graph. So as I was saying, this topic is still graph, but it's a more formal aspect of graph where we are now defining the type of equations in terms of either a function or a relation. So we're going to start off looking at first what is a relation, and then we move on to look at what is really a function. All right, so a relation. Now, a relation is a set of ordered pairs. Now, you may look at this set of ordered pairs and maybe you may identify something about the ordered pairs. What do you notice about the ordered pairs?
So they can divide into the other ones.
Well, all right. So, but that's not exactly what I'm trying to bring across. If you look at this set, you will actually see that it's a set of coordinates.
Mm-hmm.
Right? Now, remember, we refer to our coordinate, and our coordinate system follows a special order. If we are writing two numbers as coordinates, it will follow a special order. We first write the x coordinates, then the y coordinates. So every time we look at a coordinate pair, we know that the x value comes first and the y value comes second. And so that is why we call them ordered pair, because we have to follow that order. All right, any question about that, guys? So this is a set of ordered pairs. And we refer to the set of ordered pairs of how they have some kind of relation. Now, if you consider what we were doing when we were plotting graph, we know that in order to get the y value, we would have to use an equation with some x values. And so that's a relationship they share. The x value would be what we refer to as the independent value, but the y value would be the dependent value. So it means that the y value would be dependent on the x value. So if you put that x value into an equation, then what will come out as your output would be your y value. And so that's a relation. So the relation then is the equation that you use to calculate an x value to give you a y value. So that's a relation. So in other words, equations are really relations. And so they relate your x values with your y values. All right, guys, is that clear? So
Go again, please.
So I was saying to you that these set of coordinates, they follow an ordered pair. Now, in our coordinate system, we generally have our X value first, then our Y value after in the coordinates. Now, how do we get our Y value when we are calculating our coordinates? Remember, when we use our table, when we're doing graph, we would have chosen a range of X values. We plug in those X values into an equation and we calculate them using a table, and what we get after we calculate would be our Y values. And so our coordinates would be our X values paired with our Y values. So I'm saying to you that the relationship that X and Y has is their equation. It is the equation that relates both of them together. So if, for instance, so let's say this relationship here, so all right, what were you saying about how these values are related, Ms. Wilson?
I was referring to the second and the third one. I was saying that the 4 can be divided into the 8 and you get half, and the 2 into the 4 you get the half, just the same.
All right. So we can say the relationship here is that Y is equal to half of X. That's a relationship, you know. Y is equal to half X. So in order to get your Y value, you would put in your X value. So when X is 0, Y give you half of 0. You would get back 0. When Y is equal, when X is equal to, when X is equal to 4, then Y is equal to half of 4. And so you will get 2. And when X is equal to 8, Y is equal to half of 8. And you will get 4. So if you continue on the same trend, you will see how we get the Y value here to be 5 and the Y value here to be 8 for the next 2 coordinates. All right, so we are saying that the relationship between X and Y is this equation, right? So this is how they relate. For every X value, you get to get the Y value, you would have to plug in the X value in this. And that's what we were doing when we were doing graph. You know, we were actually plugging in the range of X values in the table and calculate the Y values. It's the same thing, right? So we are referring to the relation here as the equation that you plug the X into to get out the Y. You get what I'm saying now, Ms. Reza?
Yes, sir.
Okay. So it means that there is something that you always do to the X to get the Y. And that's why in graph we call X the independent variable, because you are not the X value are given, but the Y values would be based on the calculation from an equation when you put in those X values. All right, so now formally the set of X values, which would be the set of first elements here, we refer to these as the domain. The set of Y values, which would be the second element, we refer to them as the range. And so the domain would have values 0, 4, 8, 10, 16. And the range, which is the Y value, would have 0, 2, 4, 5, and 8. Is that clear so far, guys? Raise your hand if you are following clearly what I'm doing. All right. Is Mr. Lamar there? Are you following Mr. Lamar? Ms. Brown, are you following? All right, so I'll take your silence to mean that you're following.
Yes, sir.
Okay. All right, so if we're to show our relationship using a mapping diagram, now we would generally use one column for our domain and one column for our range. Now the left column is our domain and the right column is our range. And our mapping diagram, we will map arrows from our domain towards our range. So based on the relation that we have just established, we are putting in the X values, we're getting back out the Y values, which would be the set of values in the range. Now, the values of the domain and range are mapped by arrows, right? Note, the domain and range are the same as the X and Y coordinates. Any questions so far? Guys, raise your hand if you understand what I'm saying. Yeah, okay, Ms. Cabrera? Okay, good. All right, so moving along. So the relationship between the domain X and the range Y may be written in the following way. Now, so you will see a relation written in this way, where it is, when you see the relation written like this, it reads X is mapped onto 3X plus 2. So you can say that the arrow means is mapped onto. So once you see the arrow, you can read it as is mapped onto. All right, Mr. Lamar, you want to say something? Or you can lower your hand. All right. So, so you will come across us writing relation in this form. All right. So this is saying X is mapped onto 3X plus 2, meaning that for each X value, to get the Y value, we substitute the value for X into the equation, right? So in other words, you can construct your mapping diagram just by plugging in your X or your domain values. You calculate them one at a time in this equation. For instance, if you have an X value to say X is 0, and you're using the relationship X maps onto 3X plus 2, then when X is 0, to get so X is 0 would be a domain value. So to get the value of the range, which is a Y value, you just plug the X into the equation, substitute the X value here would be 0. You substitute it for X, and then you do your calculation. So it's 3 times 0 plus 2. So your Y value, which is a range value, would now equal to 2. All right. And so if we have X equal 1, we will do the similar thing. And then our calculation, the range will be equal to 5. If you have X equal 2, the range equal to 8. So the X values will be the domain and the Y values will be the range. All right. Any questions so far, guys? All right, moving on to our next slide. All right, so it means then we can actually draw a graph using a mapping diagram. right? Because we know that the set of X values, those are the domain, you will put those on the X-axis. And the set of Y values, those are the range, and those will go on the Y-axis. So for the same values that we had in the relation that we start off with, the very first relation, the coordinates that we had, when X is equal to 0, Y is equal to half of 0, which is 0. When X equal to 2, Y is equal to half of 4, give you 2. When X equal to 8, Y is equal to half of 8, give you 4. When X equal to 12, half of 12 give you 6. Then you have a half of 16 give you 8, and so on. All right, so this would give you a graph of our range, our domain, and our range. Just in a similar way when we are doing graph. We just plot our X values with our Y values. All right, so just to remind you now, if the range would be referring to as the Y values, so we would put them on the Y-axis, and the domain would be the X values, so we put them on the X-axis. All right, guys, any question? All right, so I guess no, there's an error right here, guys. So I think this should be 10 here, not 12. So it's a typo, something that I need to fix. All right, so I'll clear this and move on, guys. So now that we understand what's a relation, now we want to look at what we mean by when we refer to functions. All right, so functions. Now, bear in mind, functions are relations, but there are special types of relations. So a function is a relation, which is a special type of relation. Why is a relation that is a function special? Now, it has certain properties. So relations that are functions have certain properties, and that's why we call them functions. So what are the properties? Now, they are mapping, when we're mapping functions. Now, looking at the definition here, a function is a relation in which each element in the domain maps onto one and only one element in the range. Now, using the mapping diagram, I will illustrate what we really mean by a function more clearly. All right, now the mapping of a function can either be a one-to-one mapping, or it can be a many-to-one mapping, right? Now, a function cannot be a one-to-many mapping. All right, so if you have a relation that gives you a one-to-many mapping, then we don't classify that relation as a function. That relation would just simply be a relation, but not a function. All right, so remember though, all of these would be referring to as equations. So you can have equations that are functions and equations that are relations that we don't consider to be functions. All right, so a one-to-many mapping is a relation, but is not a function. So we don't call a one-to-many mapping a function. We just call it a relation. All right. The function may be shown in the mapping diagram below. So here, this is a mapping of a function. Now, if we go back to what the definition of a function is, we say that each element in the domain will be mapped onto one and only one element in the range. Now, the question is, from this mapping, can you say that this mapping fits the definition of a function? Each element in the domain maps onto one and only one element in the range. With that said, would you say that this mapping is a function? Anybody?
Sure. It says that each domain do what?
Each element in the domain, each X value in the domain maps onto only one Y value in the range. That's what it is saying. So I'm saying, looking at this mapping, would we classify that as a function?
No, sir.
All right. Now, it may be a little confusing at first, but as we move along, we'll clarify it. All right. Anybody else want to make any comment or add to anything that Ms. Wilson just said? All right, so let us check and see. Each element in the domain, how many elements do 0 map onto?
1.
How many elements 1 maps onto?
1.
How many elements 2 maps onto?
1.
How many elements 3 maps onto?
1.
How many elements 4 maps onto? How many elements 4 maps onto, Mr. Lamar?
1.
1. So yes, this would be a function because based on the definition, each element in the domain must only map onto one element in the range. It didn't say that different elements in the domain can map onto the same element. It did not say that. It only says that each element must only go to one in the range. Is that clear, guys? Now, I like to use the analogy of mothers and children to kind of get this idea across. All right. So if we think of the domain as children and the range as mothers, now each child can only have what? One mother, right? But you may have 2 or 3 children having the same mother. So in this case, if these are the children over here, so this is child number 1. Child number 1 only have one mother in the range. But child number 1, 2, and 3 have one mother, but it's the same mother. Right? Now, child number 4 has a different mother. Right? So each of these child will have one mother, and some of them can share mothers. All right? Now, if you look at, if you remember what we had said early on about the types of mapping that you can have one-to-one mapping, or we can have many-to-one mapping. Would you consider this to be a one-to-one mapping?
No, sir.
No. Ms. Waysam, are you following?
Yes, sir.
All right. So if this is a function and it's not a one-to-one mapping, what kind of mapping is this?
Relation.
No, it is a function, but what we're saying is two types of mapping I described before. So you can have one-to-one and many-to-one. So Mr. Lamar says that this is not a one-to-one. So what kind of
It's a
mapping?
many to one, sir.
All right, so it is a many-to-one, but here, this is why we call it a many-to-one. Because if you look at child number 1, number 2, and number 3, these are many children going to one mother. So this is many in the domain to one in the range. So this is a many-to-one mapping. Is that clear?
Yes, sir.
Right. Now, we would not expect this to be the mapping of a one-to-one, because what would be obvious about a one-to-one is that one child have one mother and no two or no more than one child shares more than one mother. All right. And so that would give you a many-to-one. This would give you a many-to-one, but the other one would give you a one-to-one. All right. Any question, guys? All right, so the relation shown in the diagram below is not a function. Now look at this one. Oops, sorry. Is this a function? Well, it already stated that it's not a function. So I would ask you, why would you consider this mapping not a function?
Sir, because the two is sharing two different ranges.
In other words, this is one child that has two different mothers. And that can only work if they are not biological. You can't have a single child having two different biological mothers. You follow what I'm saying? Because one child cannot have two mothers. So because of that, this is not a function. So wherever you have, so this is a case of where we call now one-to-many. So this mapping one in the domain going to many in the range. So one-to-many function, sorry, one-to-many relations are not functions. Over here, we have many in the domain to one in the range. So this is actually a many-to-one function. So many-to-one is a function, but one-to-many is not a function. Is that clear, guys? Now you have to make sure you understand this clearly, because there are multiple choice questions that will give you different mapping diagrams, and they will ask you to identify which of them is a function. Right? So you have to be familiar with this. All right, any questions, guys? Everybody's clear? Raise your hand if you're okay, if you're understanding what I'm saying so far. All right. All right, good. Now, moving along. Now, function notation. Now, we use these to denote function. Now, remember, notation is just a big word for symbols. So if we want to show a relation to be a function, remember that when we write it like this, we are just writing it as a relation. So we are saying that this is a relation x maps onto 2x plus 5. But if you want to show that this relation is a function, then we have to write it like this. Now, when it is written like this, we put a colon between f and x. So the f here denotes function, and the colon would mean such that. So we can say f is a function such that x maps on to 2x plus 5, right? Now, another way how we can write function, we can write f open brackets with x, which is sometimes referred to as f of x. So f of x is equal to 2x plus 5. So these are the two ways that we generally denote functions. Or in other words, we write them in a symbolic form, right? So this is how we write the function in a symbolic form. Now, remember, as I had mentioned before, when we're dealing with functions, we're still dealing with equations. When we're doing graph, we would write, instead of f of x, we would say y equal to 2x plus 5. Now, to just write it like this, we wouldn't be able to say that this is a function because we don't know the nature of how these values are mapped when we're using a mapping diagram. Now, the fact that these are referred to as function, it means that we can tell clearly whether or not these functions or these equations obey the one-to-one mapping or the many-to-one mapping. So it must be that these obey one-to-one and many-to-one. And in that case, we refer to them as functions. So we will write them in the form as f of x equal to 2x plus 5, or f such that x is mapped onto 2x plus 5. But remember now, guys, if you see this, it is the same thing as writing an equation when you have y equal to something. Is that clear, guys? Is that clear? Everybody, raise your hand. All right, so it's only Miss Ways some hand I see. Who is not clear on what I'm saying? All right, is it that you guys are not clear? Those persons are holding up your hand now. Is it that you're not clear?
Yes, sir. I'm not clear.
All right, so you're not clear. So when we were doing graph, we are used to write an equation in this form, right? Good. Right, Miss? Who was that?
Sir.
That's Miss Green?
Bro.
Right. Now, I am saying that now we are formalizing these equations and we are classifying them as either relations, those equations that can fall in the category of relations, those would not have one-to-one mapping or many-to-one mapping, right? Now, those that are classified as function will have one-to-one mapping and many-to-one mapping. Now, all I'm saying is that when we write this, y equal to something in this form, it can either be a function or it can either be a relation. We would know by writing it like this. You understand what I'm saying, Ms. Brown? But if we write it like this, this tells you that it is a function. If you write it like this, it is telling you that this relation is a function. And so we use these symbols, f of x, f such that x. When we use these to write our equation looking like this, we're telling you that these relations are these equations, they are functions. That's what we're saying. Is that clear? If we want to say that it is only a relation and not a function, we write it like this. When it is written like this, it does not tell you that you have a function. It just simply means that this is a relation and you don't know if it is a function. If it is a function, then you would have to attach the F with the colon onto it. And that will now tell you that this relation is indeed a function. So by looking at this, you know that you're working with a function. If you use this symbol instead, f of x equal to the equation, because you notice now this here, 2x plus 5, is the same thing here, which is 2x plus 5. And so if you write it this way, you write f of x with the mapping arrow, 2x plus 5, it means the same thing if you write f of x equal to x plus 5. It's just two different ways of saying the same thing. Is that clear, Miss Brown?
Yes, sir.
All right, is that clear to everybody? Raise your hand. All right, guys. All right, so moving on. So, so when it is written in the second form, so we would write f such that x is mapped onto 2x plus 5. So that's what this means. And in the second way, when we write f of x equal to x plus 5, right? And so in that case, it would be the function of x is 2x plus 5. So that's when you write it like this, we read it, the function of x is equal to x plus 5. When you write it like this, we read it f such that x maps onto 2x plus 5. All right, so those are the two different meanings to these two different forms. All right, guys. All right, moving on. All right, so the following symbols may be used to denote functions. Now, so some function we can write in the form of f of x. Now, if we are identifying a different function from the one written in f of x, then we have to use another symbol like g of x. So the commonly used symbols that we use to write function would be f, g, h, and phi. So when we are writing function, we can write f of x, g of x, h of x, phi of x. And once you write them with these symbols, you know that we are referring to functions. All right. Now, the reason why we want different symbols is that we need to be able to distinguish one function different from another function. So if we're talking about f of x, then we will know that g of x is not the same as f of x, but it's a different function. All right. So with that said, guys, so we'll have h of x, phi of x. So notice that all of these would have different outputs. So this one would be 2x plus 5. This one would be 2x plus 8. This one is 3x plus 10. And this one is 6x. And so that means there